Okay. All right, cool. So back to what I was saying before, we're actually splitting up the content over 2 weeks. So we'll just jump right into the topic this week. So this week it'll be talking about graphs, talking about BFS and DFS. And then next week we will do even more graph problems and we'll talk about topological sort. So that'll be the split of graph content, and hopefully that gives you more than enough practice with graphs so you're really comfortable with them by the end of these 2 weeks. All right, so really quickly, what we'll go through in this class is we'll do an overview of graphs, we'll do an in-class walkthrough, and then the rest of the class time will basically be the breakout session. Oh yeah, and someone asked if we have class this Saturday, so we actually are having class this Saturday. And if you can't make it, make sure to report that absence, but I'll be around and I'll be teaching on Saturday. Okay, cool. So with that being said, the two types of graph problems that you'll generally see in an interview is when one, it's explicitly stated in the interview question that you have to work with a graph. So for example, one of the homework problems you did with the bipartite graph is an example of this. But more often, what I generally tend to find through personal experience is that a lot of graph problems are problems in which there is no mention of a graph, but the problem can be framed as a graph problem. So you'll probably be seeing more of these just because there are a lot more of these type of questions, and generally in real interviews, you'll get a lot more of these types of problems, the more abstract, less explicit graph problems, but you'll get practice with both of these through this week and next week. So if you ever notice in a problem you're given that there's some binary relationship between objects that can be modeled as nodes and edges, it's good to keep in mind that you might be looking at a graph problem. And a few common themes I generally see with graph problems are if there's a talk of dependencies, traversing through a grid or matrix, you'll generally use like a BFS or DFS search on that. And also a common theme amongst graph problems are if you ever have to find groupings within a graph you're given. So those are really key words you want to remember, and remember that you might be looking at a graph problem. And just as a note, on LeetCode, graph problems actually pop up with multiple different tags. So they're not really simply just in the graph tag. You'll actually see graph problems in like the DFS or BFS or union find or topological sort tags. So there are actually like a ton of different type of questions that are solved with like BFS or DFS or graphs. And a common question that I'll get is like, if I'm given a graph problem, how do I know if it's a graph problem? So graphs are generally a really versatile data structure. So if you take a look at all the problems we're doing this week, you can see that they can pop up all over the place. Generally, when I'm unsure, I'll try to analyze a problem and think, is there some way I can use the graph to represent the problem? Do I know of any graph algorithms that might help me solve the problem? And the other thing that is also pretty helpful is if I'm seeing a problem that's being phrased in some kind of a graph representation, which we'll cover in a few minutes, then that's also a good hint that I'm looking at a graph problem. So if the interviewer is giving me input that's like basically in graph form, basically you're looking at a graph problem. And more specifically, we'll go into the details of that later. Okay, so before we discuss general algorithms, it's important that you know the common terms that we use to describe graphs. So graph simply is composed of nodes that store some value. So they're similar to trees, and there are edges between those nodes. But the key thing to note about graphs is that there may be cycles within graphs. So in trees, there are no cycles, and graphs, there may be cycles. And with the edges themselves, sometimes you'll be dealing with graphs that have no direction, but sometimes you might be dealing with graphs that have a direction. So it's important to kind of clarify with your interviewer what kind of graph you're dealing with. So the common types of graphs you'll come across are directed graphs, and directed graphs are graphs in which there are directions associated with each edge. So in this case, you'll see that even though it looks like there's a cycle, because of the way the edges are directed, there's actually no cycle there, because there's really no way for a node to trace a path back to itself for any of the nodes. But on this graph on the right-hand side with this undirected graph, because there's basically a path from each node back to itself, it's a graph with the cycle. So if you're trying to model a problem with a graph, you want to use directed edges to model one-way relationships. So for an example, dependencies would be modeled using directed edges, and undirected edges would be used to model bidirectional relationships. So hopefully like your friendships are bidirectional, but that's like a good example of something that you would use an undirected edge to model. Aside from that, a common term we also use to refer to graphs that have no cycles are called acyclic graphs. So when you're working with graphs, remember to ask your interviewer if you have to deal with cycles. So sometimes you get lucky and your interviewer tells you, you can assume that the input you're given is a graph with no cycles, and that really simplifies the problem space you're solving for. And also it's interesting in the case of like a directed graph, as I was saying before, that in this example, there's actually no cycle there. But in this example, this is a cyclic graph. If you merely change the direction of one of the edges, now there's a path from every node back to itself. And I think the most common bug that I see, or personally that I experience with graphs, is as I'm traversing them, it's really easy to get caught in like an infinite cycle. So when you're coming up with a solution or you're going through your solution and you're trying to debug it, make sure you have the ordering of when you insert something into like a visited set properly, and you're always checking that visited set before you traverse a new node so that you avoid ending up in this infinite loop. Yeah, someone asked if a directed graph can be modeled as a bidirectional relationship, and yes, you can. And in that case, you would have edges pointing in both directions. So if like foo and bar have a relationship both ways, then you would have an edge from foo to bar and from bar to foo. So you just have to create both edges to make that a bidirectional relationship. And that's something you see pretty frequently too. Okay, cool. So now that we've covered the fundamentals of graphs, it's also really important that you know the three most common graph representations. And the reasons that you should really know these well is because sometimes you might come across a problem. Actually, oftentimes I see a lot of problems where you see like a graph being represented in one of these forms, and you'll see it in like the way the problem is phrased, and it gives you like a huge hint that basically you're seeing a graph problem, even though it's like one of those non-explicit graph type problems. So that's one of the, I feel like that's the biggest reason you should know it. It really helps you be able to easily match like abstract graph problems to graph algorithms that you know. Another thing is, whenever you come across a graph problem that's where it's very explicit that it's a graph, the interviewer might give you the representation in one of these three forms, and you don't want to be learning these representations on the spot. So hopefully by the end of these 2 weeks, you're really comfortable with all three representations. So if you ever get one of these problems in an interview, you'll know like you're very comfortable knowing how to map like the representation to an actual diagram of the graph, and you're really comfortable working with all the different representations. All right, and lastly, sometimes when you're dealing with these abstract problems where it's not explicit that it's a graph, you'll possibly have to construct a graph on your own. So you should be comfortable taking an input and constructing the graph that you need. Okay, so the first representation I'll talk about is an adjacency list. And adjacency list is a mapping of the node to the nodes that they're connected to. So in practice, this looks like a dictionary where the keys are the nodes and the values mapped to those nodes are basically the list of nodes that the key is connected to. So in this graph, for example, the adjacency would look like this. The adjacency list would look like this, where node A maps to node B and C because there's a edge going from A to B and A to C. And then if you kind of go on for each node, that's how you build up the adjacency list graph. All right, so the next representation I think is a bit easier to understand because it's simply literally like a list of edges. So each edge is represented by a pair of vertices. And in a directed graph, the first vertex of the pair is the starting node, and the second vertex would be the one it's pointing to. So in this example, we have a directed graph, and you can see that because the edges are going from A to B, the pair that represents that edge is a pair of A to B. And if it's an undirected graph, then the ordering really doesn't matter of the pair. And you can have like that edge A to B, if that were undirected, represented with BA or AB, it doesn't really matter. And I think in practice, a lot of times I do see that questions tend to come in like edge list form, or like you're given an input and generally the graph is represented as an edge list. And I just think that tends to happen because it's a bit easier to like construct a graph in this way and run like create test cases. So generally I do see edge lists pop up pretty frequently. And I feel like I saved the most difficult to understand representation for last, but the adjacency matrix is basically representing a graph by an n by n matrix where n basically equals the number of nodes. And in the matrix itself, in the ith row and jth column, it's true when there's an edge going from I to j. So if we were to break down what this graph looks like in adjacency matrix form, it would look like this. And generally, I find that they can be a little overwhelming to process. So I find that whenever I'm given an adjacency matrix representation of a graph, I find that it's a bit easier for me to understand it if I try to break it down one row at a time. So in this case, if we look at the first row with node A, I would go through basically and see that, let's go through like each column. So from A to A, I guess depending on your interviewer or how they decide to define that relationship, the relationship between a node against itself might be set to 1 or it might be set to 0. I think it's actually more commonly set to 1. So that could be a 1 right there. But you see that there's an edge from A to B, so that's set to a 1 there. There's also an edge from A to C, so that's why there's a 1 on the third column. But then between D and E, there are no relationships between A and those nodes, so those are set to 0. And you basically go through each row and just construct the graph that way. So if at any given point where you want to construct like a adjacency matrix graph, I just highly recommend you diagram that out and then build it up the graph like one row at a time. All right, so there are different like space and time trade-offs between each of these representations. So you want to understand the trade-offs you're making between the different representations of the different graphs. So to pin down like what graph representation you want to use, if ever you have to construct a graph, you should have a good understanding of the common graph queries associated with graphs and also understand the space complexity for each one. And generally, when we're breaking down like time or space complexity, the way we like to talk about it with graphs are we use the letter V to represent the number of vertices, and we'll use the letter E to represent the number of edges. And then I created this whole table right here to go through really the most frequent graph operations you'll tend to use when you're running like BFS or DFS. So it's important to know the trade-offs between these representations and be able to talk about them, because if you choose to utilize like one graph representation over the other, it's really important that you're able to talk about the trade-off you made in that decision. So generally, I won't go through and talk about each one of these operations. The slides will be posted and you can look at this table yourself if you want to look through it. And it's important that you understand it. But generally, a lot of times what you'll often use are adjacency lists. And the reason behind that is oftentimes when you're dealing with a graph, you're running BFS or DFS, and getting all the adjacent edges is very useful when you're trying to traverse the graphs. And if you look at the chart right here, if you're trying to get all the adjacent edges, the adjacency list has the best runtime for that operation. All right, did anyone have any questions about this? I went through it pretty quickly. Okay. Cool. So I'll just talk about graph traversals, and then we can go through a problem walkthrough. So with graph traversals, a lot of graph problems actually don't really require super complex algorithms, but it's really important that you're comfortable with BFS and DFS. So BFS and DFS, you've had a bit of practice with last week. When with graph traversals, it's simply just really important that you keep track of the nodes you've already seen so that you don't run into infinite loops. And with DFS, it's the same as what you've learned before. You start with an arbitrary node as a root, and you explore each child node fully before you explore the next one. So with graphs, there's no real root node generally. So you can generally pick any arbitrary node as your starting node, and you just want to ensure that you go through the whole graph and visit each node so that you fully travel the graph. Because in graphs, oftentimes you might run into the case where the graph is not completely connected. You might have a few nodes that could create their own grouping, but then there might be other groupings of nodes that aren't connected to each other. So you want to make sure that you fully explore the graph by exploring each node. So in this example, if you were to run DFS starting at node A, this is an example DFS traversal of the node. And if we were to look at the code here, generally the difference is that you have a visited set. So when you run DFS starting at a start node, you want to make sure that you always check as you're trying to traverse that node in the while loop that you're not trying to visit a node that's been visited. And then if it hasn't been visited, one of the first things you want to do is add it to the visited set. So as you go through the traversal, you don't run into a cycle. And then BFS, it's simply what you've known from before with trees, very similar concept, where you will pick a node and you'll explore each of its neighbors before visiting their children. So BFS starting at node A would look like this. And the code, assuming we have like an adjacency list representation of a graph, would look like this. So it's very similar to the DFS code, and you just want to make sure you always do that visited check there. That's always like the most common mistake I see people make. And honestly, personally, it's often like a mistake I'll make if I ever have a bug in my code. It's generally that I didn't add into the visited set, or I didn't check the visited set before I tried to explore more nodes. And yeah, I guess in regards to one traversal versus another, generally BFS is optimal for our shortest path algorithms. And if you ever are given a problem where you need to calculate or want to calculate the shortest path, that's when you would use BFS. And DFS, I think, is good for analyzing the structure of graphs. Like if you're looking for cycles or bipartite graphs, I generally find that DFS is easier to work with. But in general, I think most of the questions I see, you can use either algorithm to get it right. And in that case, just pick the one you're most comfortable implementing. Like either one honestly generally works. So I'm going to take a look at the questions people have asked. In terms of converting one representation from one to another, yes, a lot of times, I guess the way I try to solve graph problems is generally it consists of two steps. One would be taking in the input, and if necessary, I'll convert that input into a graph. So I generally like to create a helper function that takes in the problem input and converts it to some representation of the graph that I find easy to work with and easy to traverse with. And then the second part of the solution will be another helper function to simply run DFS or BFS on the graph that I've constructed. So if you find that it's hard to work with, it's fine for you to convert a matrix into an adjacency list to solve the problem. Although I do think, I guess sometimes there are problems in which if you just need to traverse the graph once, you're better off just saving the space complexity and traversing the graph and not creating a separate graph representation, because that does basically use up more space. So if you run into a problem like that, then just traversing the adjacency matrix graph hopefully is sufficient. And someone asked, is it fruitful for us to review minimum standing tree and Dijkstra's? I generally have not seen that come up in interviews. So I don't think it's as useful as you going through and really understanding BFS, DFS, and topological sort. So those are the most common questions I see. Okay. Great. So I want to go through, and with the time we have in class, I want to do a quick walkthrough of a question, and it's a abstract graph question where it's not explicitly stated that it's a graph problem, but I feel like it falls in like a general family of problems where you're kind of asked to find the connected groupings of nodes within a graph. All right, so the problem I'm going to review today is called the find provinces problem. So it's a LeetCode code problem. It's a like medium level difficulty problem. And the problem statement is that there are n cities and some of them are connected while others are not. So if a city A is connected directly to city B and city B is connected to city C, then city A is considered indirectly connected to city C. And they define a province to be a group of directly or indirectly connected cities with no other cities outside of that group. And you're given an n by n matrix called isConnected, where isConnected of I and j equals to 1, if the ith city and jth city are directly connected, and it's set to 0 otherwise. Okay, so you're given this problem statement, and the great thing is if you know your graph representations, you can immediately see that you're basically given adjacency matrix, right? So it's helpful for you to know the representations because it gives you a huge clue of like the type of problem you're looking at. So more specifically, if you're given this input here, the expected output is 2. And I think this is generally hard to decipher. So what I generally like to do with interviews, this is not specific to graphs themselves, but I think Mari brought it up in a previous lecture, that it's generally helpful to have a pen and paper next to you when you're going through interviews so that you can diagram out different graphs. And in this example, you can take this adjacency matrix and write out the corresponding graph so that it helps you understand like how the output is derived from this input. So in this example here, if we were to try to build up what the graph representation looks like, we have 3 different cities because there are 3 different rows. You have city 0, 1, 2 corresponding to the different rows in the adjacency matrix. So if we were to build starting from city 0, I guess it's considered that city 0 is in a province with itself. So it's set to 1 there. City 0 and 1 have a connection. So that's where there's an edge there, but city 0 and city 2 don't have a connection, so we don't create an edge there. All right, so if we go to city 1, we see that city 1 has a connection to city 0. So you can see that this is an undirected edge relationship. So that's why in both those entries between 0 to 1 and 1 to 0, you'll see a 1 being set there. And across the diagonals, which are basically the cities themselves, those are also set to 1 because each city on its own is considered to be in its own province. And then lastly, city 2 isn't connected to any of the other cities because if we look at the column 0, there's a 0 there, column 1, there's a 1 there, and then it's in a province with itself, so that's set to 1 down there. And that's how we get the output of 2 over there. So going through an example is really part of the like understand step of umpire. but it's also really important to construct your own examples just to kind of add extra test cases and make sure you understand what exactly the problem is asking you. And generally with these abstract graph problems, I find that it's really important to construct your own examples just to verify between you and your interviewer that you really fully understand what they're asking you to do, and you really understand how the output is being constructed off of the input. All right, so I think a good example to generate that I would want to test in this case would be an example where the cities are all in one province. So specifically, I think this graph would be really helpful for me to test my code and to make sure I really understand the problem itself. And I think that's a good case to go through because basically it tests an indirect connection where city 0 is not connected to city 2, but is connected to city 2 via city 1. So if we were to convert this corresponding input or like diagram into the adjacency matrix representation, we want to go through it city at a time. So with city 0, it's only connected to, basically it's connected to itself and it's connected to city 1. So the input for city 0 or the row corresponding to city 0 would look like this. And then we'll repeat this process with city 1 and city 2. So city 1 is connected to 0 and connected to 2, so it's set to a row of 1s. And then city 2 is only connected to city 1 and itself. So that's why in the first, or I guess the column corresponding to index 1 and column corresponding to index 2 are set to 1s. And the output of this example would be a 1. So I will generally store this as a test case that I want to use later. Does anyone have any ideas of what test cases they would ideally also want to test against this problem right here? Yep. Okay. Someone mentioned just a few, I think, important cases that you want to cover is the case where no city is connected to each other. So every city is its own province. And a case where a matrix where like all the cities are connected to each other, I want to make sure that my code doesn't break in that case and I don't run into an infinite loop in that case. And for other cases, I basically want to just use the ones I create and make sure that my code runs against those. All right, so we kind of actually did the match step where we were able to narrow this down to be a graph problem, but it's also important to try to figure out which graph algorithm we'll use against this problem. So if we think about this problem, it's effectively asking you to find all the connected components in a graph. And in this case, a province is basically a connected component. And what a connected component is basically a group of nodes where there's a path from one node to every other node in that group. And you can basically accomplish this by traversing through the entire graph and try to find connected components while you are going through this traversal. And between BFS and DFS, we just generally need to traverse the whole graph and do some bookkeeping to track the number of groups we're seeing. So either algorithm will actually work in this scenario. We're not trying to compute like the shortest path or anything. So there's no like preference between BFS or DFS. And in this case, I'm going to attempt to try to solve this problem with DFS. All right. So onto the plan step. So if you decide to run DFS to solve the problem, how do we use DFS in this case? If we take a look at an example, let's say we were to start running DFS with node 0, we would then traverse to node 1. And after we traverse to node 1, we'll basically end because there are no connections to any other cities. So as we're kind of traversing through the graph, we want to make sure we mark the nodes as visited before running DFS on all its connections. So we'll need some visited set. But also during the DFS, we want to track the number of components we see. So in this example, when we visit node 0, which is a new node that we haven't visited, we want to increment the number of groups that we've seen so far because we're now visiting a new grouping. And when we want to run DFS on node 1, we would then So we basically want to start at node 0. We haven't seen 0 before. We'll be sure to increment the grouping count because this is like a new province that we see. We want to start fully exploring all the different nodes that are reachable via node 0 and mark them as visited so we don't end up double counting provinces that we've seen before. And once we've kind of fully explored all the cities that are reachable from city 0, then we can move on to new nodes that we're, or new cities that we're evaluating. So basically, you're basically running DFS and also keeping track of this number of provinces variable and updating that accordingly. So every time we run DFS, or like we're starting a new run of DFS on an unvisited node, that's guaranteed to be a new group of provinces we haven't seen before. So we'll increment the number of components anytime we have to start a DFS run at a new node. All right. So basically in pseudocode, what this will look like is for each node, I use node and to refer to city. I use them interchangeably, but I generally like to call them nodes. I'm more comfortable calling them nodes. So node just means city. So for each node, if we haven't seen the node before, then we want to increment the provinces count by 1 because we're starting to explore or fully explore a new province that we haven't seen before. And then we'll be sure to mark it as visited, always mark it as visited, just because you don't want to end up like double counting provinces or ending up in a infinite cycle. And then you'll run DFS on that node. And generally, I like to split up the DFS code into its own helper code or a helper method, because I feel like that makes the code a bit more readable and it's a little easier to organize my code around that. And then at the end, when we have gone through all the provinces, then, or sorry, if we've gone through all the cities, ideally the number of provinces count has been incremented properly and we'll return that count right there. And then aside from that, I left out a big chunk of code, which is basically the DFS part. So generally the way I like to implement DFS is I like to have it as a separate helper function. And what I'll do is it'll generally take in a specific node, it'll take in the matrix or the graph itself, and then it'll also take in the visited set. And the role of this helper function is basically just to fully run DFS starting at the node I pass in. So the DFS function will basically go through each of the node's neighbors. And if the neighbor has not been visited, it'll just run DFS to basically fully mark all the nodes I visited starting from the starting node that I feed in right there. So that's the pseudocode. And I'm going to try to actually implement this code. So I'm going to pull up Replit, and I actually already took in the pseudocode and I inputted it there. And then I also took in some example test cases and put it in there. So the way I would code this is I would actually go through and type in the function that I want to implement. Can everyone see, or is the size good enough for everyone to see? Okay, cool, great. All right, so what I'll do is I will take in, I'll call it a graph because it's a bit easier for me to understand. I have to make sure that I create the visited set here. And then basically what I also want to do is create like a I don't want to overshadow the name. So provinces equals to 0. And basically what I want to do is for each city in the range of the length of the graph, what I then want to do is check to see if I visited the city or not. So if the city is not, writing pseudocode, not in visited, then I can go ahead and mark the provinces equal to 1. And then I want to make sure that I add in the city into the visited set. And then after that, I'll want to run DFS. And DFS, I'll generally tell the interviewer, I'm going to implement DFS separately in a helper function. Is it okay if I just define this for now and then implement it later? So I'll define the DFS to be basically taking in a city, the graph itself, and then the visited set. And at the very end, once we've run DFS or try to run DFS on each of the cities, then we can return the number of provinces. Okay, cool. All right, so going on and actually implementing DFS, which is the core of the problem. So it'll take in a city, the graph, and then the visited set. And basically what I want to do is I want to grab all its neighbors and I want to check to see if there is, well, so we're given an adjacency matrix. So we actually have to go through, and because there is that list of basically all the possible cities, I want to filter out the cities that it's actually connected to. So I actually have to go through and grab the potential neighbors. And I will grab that. So it's actually the graph with the city. Someone asked if DFS has to return the visited set. We're passing in the visited set. So yeah, it's passed by reference. So if we're updating the visited set in the DFS function itself, then we don't have to return it because we're simply modifying the same visited set every single time we're running this algorithm. So if we go through and grab the neighbors themselves, what we then need to do is basically we want to go through and for each index, and each index kind of refers to the city itself. We also want to grab the value associated at that index. That'll be a 0 for if it's connected or 1 if it's not connected. So Python has like a nifty enumerate function that'll give you the index and the value at that index of a row. So I'll use that index basically, and then is neighbor. Enumerate the neighbors itself. What I then want to do is if it's not a neighbor, so if you're not looking at a neighbor, then you continue, you can skip this specific city because the city is not connected to this potential neighbor city. Otherwise, what you then want to do is check to see if, so now we're hitting the case where, yes, like the city we're looking at this index is actually a neighbor of the initial city we're passing in. And we just want to make sure that that city is not in the visited set. So if the index, which corresponds to a city, is not been visited, then what we want to do is we then want to go ahead and make sure we add in visited.add index. And we want to make sure that we fully explore the province starting at this unexplored city. So we want to then go ahead and run DFS starting at the index, the graph, and passing in the same visited set so that we're using the same visited set as we're running DFS across the whole graph. And I believe that should be it. Generally, after I code, I also like to just take a look at my code and make sure that I don't flag any, nothing major is missing. Okay, great. So generally, you might be asked to actually run your code against the input. So what I'd like to do is then to run against this input, which should output a 2. So I like to run it really quickly. Okay, so that looks good so far. But then I like to run it against the cases we talked about. So in the case where none of the cities are connected to each other, we want to make sure that this outputs a 3. Okay, that looks good. And then we just want to go through and run through the case that I brought up before, which is when the cities are all connected to each other, and that should return a 1, and hopefully that doesn't loop. Okay, great, that looks good. All right, so the last thing that you generally need to do when you are going through a problem is if the interviewer So generally you'll verify your code, and then if your interviewer wants you to run through their own test cases, they'll probably copy and paste them and ask you to run it, and just to really make sure that your code works. And after that, they'll probably ask you for a runtime complexity of the code that you've written. So in terms of space complexity, all we're really creating is the visited set. So at most that will basically be O of n, where n is the size of the graph, which is basically the number of cities that are in the graph. And then aside from that, we actually aren't creating anything else. So that will basically be O of n space complexity, where n equals to the number of cities. And then as for time complexity, we're actually simply just traversing through this n by n matrix once. So that'll give you O of n squared time complexity. And someone asked, do we include the recursive stack in the space complexity? I think generally when I'm running space complexity, I don't talk about that. But then if the interviewer brings it up, or I mentioned that, maybe like if I want to bring it up, I'll also bring up that separately. So I'll do that analysis separately. And then generally, like if your interviewer asks you about the recursive stack, you can also say like, one optimization you could also make is running this iteratively instead of recursively. And someone asked if there's a good DFS code template. I can try to take a look and see if there's a good example and try to put that out if I see any. I probably will just go online and look at like DFS code for graphs on Java. And yeah, I guess with the remaining time, I want to give you enough time to go through practice problems. And I also wanted to really quickly talk about disjoint sets, which we don't really cover in this course. But this type of problem where you're asked to find like the number of groupings that exist in a graph, it tends to pop up pretty frequently, and it'll kind of look different depending on the problem. So a lot of times, like they might ask you to find the number of groupings. Sometimes you're asked to kind of synthesize all the groupings into one. That's also a different type of problem I've seen, but it's effectively solved in a similar way. So I just want to mention disjoint sets. If anyone is curious or they've worked with disjoint sets and they like working with disjoint sets, it's a data structure that allows you to solve these types of problems. But I think one thing to note about disjoint sets is you want to be really comfortable implementing it, and you really want to know it. And if you really wanted to use it, that's totally fine. Just make sure that when you learn disjoint sets, you also learn path compression, because that's the most optimal way to use it. And I actually linked to some guides and some interview questions if you're curious about disjoint sets. I just want to throw it out there so that everyone is familiar and knows it if they're pretty curious about this. All right, that being said, we'll basically spend the rest of class doing breakout session. And for a breakout session today, it'll just be kind of you working as a group trying to solve 3 problems. Mostly it's more important that you get through the first 2, and the bonus question is a bit more challenging. And if you have any questions, feel free to ping me or let Daphne know, and I'll jump into the room. And with these problems, I want everyone to kind of take turns and make sure that each person has the opportunity to lead the problem or to code the problem. So if someone hasn't had the opportunity in the past, make sure everyone gets their fair opportunity to practice that. And I want everyone to use the Replit to test their code and not rely on LeetCode, just to make sure that you're really comfortable testing your own code.
Goodbye.